Yeah, so my name is Ian Jones. I'm in the Gravity group here in Southampton, and my talk follows on, I hope, rather nicely from Manda's. So Manda told you about what we've learned about black holes mainly from light, from the electromagnetic spectrum, and she mentioned gravity and gravitational waves a few times. In a sense, my talk is the flip of that. I'm telling you about black holes, but I'm going to concentrate very much on what we've learned of them from what is really a new branch, a new sort of astronomy that we're doing that uses gravity itself, called gravitational wave astronomy. So let me paint the scene. Um, so back in 2015, something really exciting happened, probably the most exciting thing of my career. And I'm going to tell you all about this in the rest of the talk. Really, the rest of the talk is fleshing this out. But something called the LIGO experiment detected little ripples in the gravitational field that we claimed were coming from two colliding black holes. And you can see in this sort of schematic on the slide here, you can see two sort of waveforms, two little sort of squiggly curves. And these are the outputs of the two separate LIGO detectors. And our claim was that that squiggle there represented two black holes orbiting around one another and eventually colliding to form one bigger black hole. So this really was quite big news at the time. I did a little calculation and it made me feel terribly old. This seems like yesterday to me, but I've worked out that, assuming that some of you are in year 12 now, some of you might have been 9 years old when this happened. So you probably won't remember any of this, but this was big news at the time. I downloaded PDFs of some of the national newspapers on the day that so this is in February 2016, we announced our discovery. And these are the front pages of a few newspapers, so you can see the Independent gave a full page to it. Theory of relativity proved. Technically, as a scientist, you don't like saying things like that. We're in the business of sometimes disproving things, but I don't know if we ever really prove physical theories. But this was proving one of the predictions of Einstein's theory of relativity. Here's another newspaper. This is the Daily Telegraph. Again, you can see a lot of that front page devoted to it. This is back in the days before Brexit, and so there's loads of stuff about that as well. But there's a lovely picture there. Needless to say, right? That's not a real picture. That's an artist's impression of something or other there. And even the big issue got in on the act, and that was the front page of the big issue immediately after we made this announcement. So you can see like an astronaut floating in the foreground, and then there's Einstein at the top shouting it's cosmic with his tongue sticking out of his mouth for some reason. So there we have it. This really was big news. So what I want to do in my talk is tell you, or try and answer a few questions really, and what I want to explain is what are gravitational waves? Why was this detection of these by the LIGO experiment such a big deal? So that's what I'm going to try and tell you about. I'm going to start this story a long way back, much earlier than 2015, because this really is an old story. In fact, I want to go back exactly 100 years before we made this detection. So back in 1915, Einstein published his theory of general relativity. General relativity was basically his theory of how gravity works. And you'll have studied about gravity, I'm sure, at school, and you probably learned a bit about Newtonian gravity. And of course, you'll have been taught to think of it as a force, right? You know, it's a force and it acts on masses and it accelerates them. And that's a perfectly good view of gravity. But to go to the next level, to go to Einstein's theory, he taught us to think about gravity in a very different way and in a rather mysterious way. So back in 1905, with his special theory of relativity, he taught us to think of time and space not as separate things, but as something called space-time. His big new idea in general relativity was that space-time, in a sense, is curved. And you can see in this little picture there with those red curves that objects then follow what are called geodesics, like straight line trajectories within this curved space-time. Now, that's a really weird and peculiar idea, and I'm not going to go on about that too much, but one of the other main big things to come out of his theory of relativity was that nothing can travel faster than the speed of light. And from what I want to tell you about right now today, this has got two important implications. So let's start with the first one. So the first one is it naturally led to the idea of a black hole. So a question came up about this in the chat. Let me give you one way of looking at it. So, right, 1959, Einstein published his theory. He thought it was so complicated, people wouldn't be able to work out its consequences very easily. But the very next year, someone called Carl Schwarzschild found a mathematical solution that no one called it this at the time, but he called it a black hole. And the fundamental idea here was if nothing can travel faster than light, what you could imagine doing is like taking, say, a star, and you could imagine crushing it and crushing it. And the more you crush it, the stronger its gravity at the surface gets. So if you were to then throw something up from the surface, well, it will travel up, 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 come to a stop, and then come back down. But if you throw something fast enough with what's called the escape velocity or higher, then it can escape to infinity. So you can always imagine like standing on the surface of a star or a planet, and if you throw something fast enough, you can throw it away and it will keep going forever. The point is this, that if there is this cosmic speed limit, if nothing can go faster than the speed of light, then there's a limit to how fast you can throw anything up. And it suggests, and this is basically what you can think of as lying behind the Schwarzschild solution, that if you crush your star enough, the escape limit would exceed the speed of light, and that's when we get a black hole. This is a rather qualitative hand-waving thing, but it's a nice sort of picture that's got some truth to it to understand why we think black holes are real. And what you can see in these pictures here, so on the left, it's an artist's impression of an accretion of a load of gas falling into a black hole, just like the sorts of things that Manda spoke about. I'm actually going to be thinking about rather smaller mass black holes, like a few tens of solar masses, but the principle is the same. We can see black holes in the electromagnetic spectrum with light. When gas falls in, the gas gets hot, and we see the light from the glowing gas. And that right-hand image, this right-hand image is a real astronomy picture. And one of those little dots there, the one that's labeled Cygnus X1, that was the first confirmed X-ray sighting or first sighting observation of a black hole. So that was quite an important thing. So that gave us confidence that black holes existed, but only by seeing the gas falling in. All right, so that's one of the two important implications of there being this cosmic speed limit. The other one is to do with the gravitational waves themselves. So you know that the Earth orbits around the sun, and it's held in place, we normally think of by the force of gravity. So suppose the sun was suddenly whipped away, what would happen? So you might think that immediately the Earth would no longer feel the attractive gravitational force of the sun pulling it in, just like, whizzing a stone around on a piece of string and someone cutting the string. You might think the Earth would sort of go whizzing off in a straight line, but it's not quite what would happen, again, in this simple sort of thought experiment. What Einstein's theory tells us is, well, there is this cosmic speed limit, and his theory predicts that even gravity itself has to obey this speed limit. In other words, when the sun disappears, when everything moves around, the gravitational field that it produces doesn't change instantaneously. And if you actually look in the details of Einstein's equations, you see that change in gravitational field propagates out as a ripple in the gravitational field, as a wave, a gravitational wave. And if you do the mathematics, you see indeed it travels at the speed of light. So that's the second sort of big implication. And what you can see on this schematic here is a picture of like two stars, and maybe they're two black holes orbiting around one another. Again, it's an artist's schematic, but the idea is they're producing changes, these little ripples in the space-time that are propagating outwards. And it's those things that we call the gravitational waves. Okay, so that is our sort of starting point. That's what the theory tells us. It tells us that we think black holes should exist and that changes in gravity should travel as gravitational waves. Both predictions from way back from the beginning of the 20th century with Einstein's theory of relativity. So then one would wonder what produces these gravitational waves, I can see the title of this slide is slightly covered, but it's what produces gravitational waves. Well, really, any sort of motion pretty much of masses will produce gravitational waves. So just moving your arms around produces gravitational waves. But if you put the numbers into Einstein's theory of relativity, what you find is that the things that go on here on the Earth, in the solar system, our gravitational fields are so weak that the gravitational waves that we generate are completely insignificant. What you find when you do the calculations is that you need really violent astronomical events to produce detectable and interesting levels of gravitational waves. And that's what this slide is all about. We actually think of there being four qualitatively different sorts of types of source of gravitational waves. So the thing that you can see top left, I've called colliding compact stars. It's the idea here, well, it's the thing I just mentioned. You've got two stars in orbit about each other. If these stars are really small and dense, maybe you say they're two black holes, then they can get really close to each other without touching. So you can have a really sort of tight, fast orbit. That could produce quite a lot of gravitational waves. Gravitational waves themselves carry energy. The question you can then ask is, well, where does that energy come from? I mean, general relativity respects energy conservation like the rest of physics. Well, there's only one place it can come from, and it's the orbital energy, what we call the orbital binding energy of the system. It turns out that if you want to decrease the binding energy of this orbit, then the two stars have to spiral together. And so the picture that we've got is that if you start off with, say, two black holes in an orbit close to each other, and they emit gravitational waves, and it causes them to spiral in, and that process goes faster and faster, and eventually then they'll collide, and they'll form one black hole, and they'll emit lots of gravitational waves in the process of doing that. And the reason I've said we need colliding compact stars is that if this wouldn't work with two of our suns, because the sun, normal star, is so big their surfaces would touch before this gets important, but it works for black holes. And it also works for another type of like small dense star, I'll come to in a moment. Top right picture, exploding stars. So Amanda mentioned supernovae, right? So when a normal star reaches the end of its life, the outer part explodes, and that's the supernova. But the interesting bit for us is that the inner part of the star implodes, and that can leave you with some small dense star. And if it's a big enough star, it will leave you with a black hole. If it's not quite dense enough, it can leave you with something that's not like completely imploded, called a neutron star. A neutron star is got something like the mass of our sun, but in a sphere of radius about 10 kilometers. So it's incredibly dense, and it's got very strong gravitational fields. But either way, when these supernovae occur and you get this collapse, that collapse probably shakes mass around a lot. That could produce gravitational waves. Bottom left, rotating neutron stars. So these neutron stars I mentioned are small dense stars. If they're sort of bumpy in some way, so the mass isn't completely smoothly distributed, then as they rotate, they'll emit gravitational waves. And we're pretty sure that there are lots and lots of these rotating neutron stars in our galaxy, and that's to do with this little sort of artist's schematic. There are things that astronomers, mainly radio astronomers, see called pulsars. These are stars that pulsate in the radio. They may go, blip, 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 a period of about a second. Some are faster. We think that they are spinning neutron stars, and they're shining like lighthouses, and that's what's shown in this schematic here. And each time the lighthouse beam swings past Earth, we see a little blip. So these things could emit gravitational waves for like millions and millions of years. Whereas the top two things, the colliding stars, the exploding stars, you might get a short burst of gravitational waves over, I don't know, order a second. Rotating neutron stars, they could produce these weak signals, but for very, very long periods. Then finally, the picture that you can see bottom right, if I was in the same room as you, I'd ask you what it was. This is a picture of the so-called cosmic microwave background. So the cosmic microwave background is a picture in light, so not gravity, but in light, of what the universe was like when it was about 380,000 years old. we would, it's telling us about the Big Bang and the physics of the universe at very early times. We would love to see the gravitational wave analog of that. And if we did, then we'd be learning about what the universe was like, not when it was about 380,000 years old, but when it was like some small fraction of a second old. So we'd get much, much closer to the Big Bang. So those are the different types of gravitational waves that we'd like to see. I'm sort of going through the history of this now. So Einstein made this prediction back in 2015. It was a while before people worked out and agreed that gravitational waves were real. But then people started to think, well, how could we sort of check this experimentally? And some people did a very clever thing. What they did was that they looked at a binary system. So it's one of these two stars in orbit around one another. And they found a binary system that seemed to contain two neutron stars. So it was really sort of small and orbiting really fast. And what they noticed, and this is the thing that's shown in this plot, which goes from like mid-1975 to about 2005, what they noticed was that the orbit was sort of, well, the period of the orbit was getting smaller, as if the orbit was shrinking. And all of those little black circles you can see, those are the data points of how some particular quantity to do with this orbit was changing in time. The line, the curve that you go through them, is the prediction of how this orbit should shrink if you apply Einstein's theory of general relativity to it and allow the orbit to shrink because it's emitting gravitational waves. And you can see it's spot on, right? There's excellent agreement between the theory, that's the curve, and the data points, the little dots. And this won two pulsar astronomers, two radio astronomers, Hulse and Taylor, the 1993 Nobel Prize. So this gave people a lot of confidence that gravitational waves were real. But in a sense, it was an indirect detection, because what we'd done is we'd seen the effect of a gravitational wave onto stars way out there in the galaxy. So people wanted to do better. They wanted to actually build a machine that would directly detect the gravitational waves themselves. So the next question I want to answer is, how do you detect a gravitational wave? So you can't feel them, but there's gravitational waves passing through you, through me, through all of us all the time. What they actually do as they go through us is that they make things shake a little bit. So they just sort of jostle you around in a bit. First they sort of squash you a bit, then you pull you out. Squash you, pull you out a bit, a little sort of tidal force. This is the key to figuring out if you can, or how to build a machine to actually detect gravitational waves. And the first person to take this idea seriously was the guy that you can see in this picture here. He's called Joseph Weber. And what he did in his laboratory in the US was he built a big metal bar, and you can see one of his bars there. And what he did was he sort of hung his bar up from some suspensions to try and isolate it from just sort of random seismic noise, just random shaking from the laboratory, so that if the bar did start to shake, he could then claim that he'd seen a gravitational wave. So he tried this, and he actually claimed back in the 60s to have made many detections. Other people were a bit skeptical, and so they tried to reproduce his experiments, but nobody could. And eventually it became clear that there was something wrong, and he wasn't really detecting them. So that was a sort of a bit of a dead end experimentally, and it sort of set the field back of gravitational wave astronomy a little, but things did then change. So one of the problems with Weber's idea was that he could only build a bar that was so big. So if I just go back 1 second, that bar is something like 1 meter in length. If he'd been able to build a bar that was 2 meters, and the effect that he was looking for would have been twice as big. If he could have built a bar 10 meters in length, 10 times as big, the effect, this tidal stretching and squeezing scales with the size of your apparatus. So the clever idea that people came up with in the 1980s and started building in the 1990s was the so-called LIGO experiment. So LIGO is an acronym. It stands for Laser Interferometer Gravitational Wave Observatory. There are two LIGO detectors in the US. So one is in the top left. That's like the northwest of the country in Washington State, and there's another one in the bottom right. So that's the southwest in Louisiana, and they're basically large L-shaped devices. So you can see all of one arm of this L and a bit of another arm, and you can see the so-called corner station, this building in the bottom right. What's going on here is very clever. There's a big powerful laser in that building, you can see bottom right, and half of its light is being sent up one arm, half of its light is being sent up the other arm, and there are mirrors 4 kilometers away at the ends of these arms, and they reflect the light back. These two beams are then combined, and I'm hoping this sounds familiar to you from something that you may have done in physics in school. When you combine two waves, you get interference, and you can get positive interference where the peaks or the troughs are in phase with one another, or you can get destructive interference. Why am I mentioning this? Why is it relevant? Well, the idea is this, that if a gravitational wave is, say, propagating through the experiment, one moment is going to sort of make one arm a bit shorter, but the other a bit longer, so that will affect the way in which the waves recombine. But then, half a period of the gravitational wave later, the situation is reversed, and the arm that was stretched is now squeezed a bit, the arm that was squeezed is now stretched a bit, and you get a change in the interference pattern. So basically, these two halves of the laser beam are recombined in this building in the bottom right, and that's the output of the detector. So if you see changes in that interference pattern, then that's a signature that you really have seen a gravitational wave. And the reason that we built two of these detectors is that then we could sort of compare the outputs of our two and look for common signals. To give you some idea of just why it took so long, so Einstein published his theory in 1915. I'm about to get to detection, but it took a century. Well, it took a century for people to figure out that gravitational waves are real, but they're really, really weak. It was a huge technological challenge to detect this. And if you read that line at the bottom of the slide, this experiment to work, it had to be sensitive to length changes in the arms of a few times 10 to the minus 15 meters. So we like to say that's something like 1/10,000th of the width of a proton. So this is why it was such a difficult engineering feat to do. You basically had to be sensitive to the tiniest imaginable changes in length. So that was the LIGO experiment. It started taking data round about the year 2000s, and I'm part of this big team, and we saw nothing, and we saw nothing, and we saw nothing. We then switched our detectors off for a few years and went in and made some changes and made them more sensitive. And then when we switched them back on in 2015, almost immediately we saw something. So the thing that we saw, we give all of these things code names. So this thing that we saw we called GW 150914. So that's gravitational wave event. It was the year 2015. The month was September, and it was the 14th of September. What you can see on this slide here, in the top of these three pictures, it's the output of the LIGO Hanford detector as a function of time. And you can see by eye, there's a little sort of low frequency, low amplitude wave at early times, and it gets bigger in amplitude, higher in frequency, and then it decays away. It's just the sort of shape that Einstein's theory predicted for two black holes colliding. We saw essentially the same thing in the Livingston detector. It was actually shifted in time ever so slightly because I said, right, gravitational waves travel at the speed of light, so there was like a light crossing time, but allowing for that, the signals were consistent, and that's what's shown in the bottom panel. If you time shift the two data streams, you can line them up pretty well and see that there really did seem to be a signal common between the two. so we were monitoring the outputs all the time, and we very quickly realized that there was an interesting signal there. So that was September of 2015. So then there was then a frantic period of about 6 months, probably the most exciting 6 months of my career, where this big collaboration set to work to really checking if we believed this result and writing it up as a paper. Now, I don't normally put abstracts of scientific papers in this sort of talk for school students, but I thought it would be nice to show you this one. So in science, the main way that you communicate your results to the rest of the world, well, I guess there are two ways. You go around and you give talks, right? But probably the main way is that you write it up as a paper. And papers start with an abstract, which is just a little paragraph that people, if they read that paragraph, they know what it's about. So this is the abstract, the summary paragraph for our discovery paper. So you can see it was published in February 2016. And let me just pick out a few things from it. If you look at the author list, it says BP Abbott et al. Abbott is spelled A-B-B. The authors are given alphabetically. You can only guess, well, you can begin to guess how many hundreds of authors there were. I'm trying to remember, I think there were about 500 authors at the time at this point. So that's why it starts with ABB, and we don't list them all. If I pick out a few numbers, the signal that we saw had a strain of 10 to the minus 21. That's the fractional change in the size of the experiment in its arms as the gravitational wave come through. We're able to figure out that it was a signal from two black holes because it had just the right shape as predicted by Einstein's theory of relativity. We could tell it was coming from 410 megaparsecs away. Parsec's about 3 light years, so this is like a billion light years away, so it's from really far away. We could work out what the masses of the two black holes were. One of them had a mass of 36 solar masses, the other 29, and they settled down into one black hole, a single black hole of mass 62 solar masses. And there's not a dumb mistake with the arithmetic there. There really is a difference of 3 solar masses between the sum of the original masses and the final mass. That is how much energy, how much E equals mc squared energy was radiated in that half a second when the two black holes smashed together. So there's no light, but it was an incredibly energetic event. So there we are. So that was very exciting. But what I want to do is explain to you scientifically this really was a big deal and why it captured everyone's attention, even in the media, so well. So my slides have been re-rendered slightly in this viewing thing, and it's difficult to read the writing on this. They were good in the original, but let me just tell you. So first of all, this was a big deal for fundamental science. People have been talking about gravitational waves for decades. As I say, the first paper on them was back in 1916. So after 100 years, we'd finally tested this prediction of general relativity, that gravity travels at the speed of light in a wave-like way, and simultaneously we'd probe black holes in a very direct way. So we weren't seeing light falling into them. We were seeing black holes in a very direct way. We were seeing them stirring up their space-time in two black holes forming one. So we were really testing, probing gravity in the strongest way possible. But then there was a second reason why we got excited, because as well as like testing fundamental physics, we were basically learning in a new way about the objects that are out there in the universe. So the phrase we like to use, it sounds rather grand, is that we've opened a new window on the universe. What we mean by that is, so for centuries, well, ever since anyone looked up at the skies, we've learnt about the universe using light. For the first time, we were using gravity itself to do astronomy, to see what's out there. So this was the first ever observation of a binary black hole system. It didn't emit any light. You had to see it this way. And it led to then astrophysicists asking lots of interesting questions, like how the binary was formed and from what, and all sorts. So it's this detection has generated lots of excitement since. And then sure enough, Nobel Prize came very soon afterwards for 3 of the project leaders. You can see them there, so people that had given a lot of their professional lives to making this a reality. Ray Weiss was one of the people that had the idea to do the experiment. Barry Barish led it. Kip Thorne So he's my academic grandfather. In other words, he's my PhD supervisor's supervisor. He was one of the people that took Einstein's theory of relativity and applied it to lots of astrophysical situations, and one of the people that made the science case that it was worth spending hundreds of millions of dollars, because there really was a good chance that we'd be able to detect these things. So that was it. That was a very exciting time. There's an so again, something's not quite rendered properly here, but let me explain. I'm going to tell you about one other exciting thing that has happened. So we've actually now seen a few of these black hole events, but we've seen one other different sort of thing. We've seen a gravitational wave signal. Let me go to the next slide. That was so I'm afraid the text is getting worse. Let me just there's a problem with the rendering that wasn't there earlier. Let me just explain in words what's going on. I'm going to quickly stop sharing this, if I can figure out how, and share it again. Just bear with me a second, just in case that problem goes away.
Yeah, sorry about that, Ian. Hopefully we can resurrect it.
Yeah, let me see, because this wasn't an issue earlier. So let's just see if reloading helps. No, it doesn't. All right. It doesn't matter. I can tell you what's going on here. For decades, astronomers had been seeing flashes of gamma ray light. They detected it with satellites, and no one was completely sure what they were. They were just given a name. They were called gamma ray bursts. But one of the theories that, as to what produced these gamma ray bursts was that two neutron stars, so not black holes, but two neutron stars, these very small dense stars, were smashing together and producing an almighty flash. Back in 2017, we saw a gravitational wave signal, and that's the thing that's shown at the very bottom of this panel here. And a fraction of a second later, some gamma ray satellites saw a flash. This was incredibly exciting. It confirmed this thing that people have been thinking about for decades, what it was that was producing these almighty flashes of gamma rays. And then there followed another very exciting time. And what happened was many of the large telescopes direct the electromagnetic spectrum suddenly started pointing at this bit of sky. So what we did is that we told our colleagues in electromagnetic astronomy roughly where in the sky we think this signal had came from, and they started pointing their telescopes at it, and it was seen in the I've already said the gamma ray, but it was seen in the X-ray, the ultraviolet, the optical, the infrared, the radio, all over it. If you look at the bottom images on this slide, you can see little crosshairs. If you look at, say, the Chandra image, bottom right, you can see two little crosshairs centered on a dot. That dot wasn't there a day before. It suddenly appeared. It's the image of these two neutron stars colliding and making those most almighty burst. So that was another very exciting time. Again, media picked up on it and reported on it. This actually gave us some very different physics insights from the black holes, because now it wasn't just gravity that was at work. It was it depended on what the neutron stars themselves were made from. So neutron stars are incredibly dense, much denser than anything we make on Earth, denser than we can't really probe these sorts of densities and things like the Large Hadron Collider. We have to sort of look at neutron stars for this. Basically, we learned something about how compressible, how stiff matter is at very high densities. We're able to do some cosmology because we could see how far away this signal had come from and what the redshift was, so we could do something to do with working out how fast the universe was expanding. I mentioned at the very beginning that Einstein predicted that gravitational waves travel at the speed of light. Well, the light signal and the gravitational wave signal arrived at about the same time, so that was verified. And then finally, we figured out that it was likely that lots of heavy elements, including lots of gold, and you can see a picture of some gold bars there, were produced in this event. And even though I think scientifically it's a bit of a funny thing to run with, that was the thing that the media and the newspapers loved. They like this idea that huge amount of gold was being produced. But no, it's not going to like devalue gold on Earth because, of course, it was happening it was happening 40 megaparsecs away. But it was quite amusing that they picked up and ran with that. Okay. We've now seen about 100 of these events. They're all binary systems, two stars smashing into one another. That's what this picture shows. The blue dots are black holes, and in the picture you can see there are sort of pairs of blue dots that connect to a higher up blue dot. The vertical axis is showing you the masses of the stars. So if you look at the far left, you can see that like a black hole of a mass of about 30 solar masses and 35 solar masses combined to give one of about 70. So we've seen nearly 100 things like that. And then we've seen a few lower mass things where we think it's neutron stars crashing together. But basically, we've now seen lots of these things, and it's almost becoming routine to make these detections. But we've not seen gravitational waves from supernovae, from rotating neutron stars from the Big Bang. So even though we've seen lots of events, we haven't seen lots of the things that we hope to see. One thing that we have seen is that people have figured out that by looking at these pulsars that I've mentioned, you can, looking at how their timing varies, you can actually make another different sort of indirect detection of gravitational waves by seeing how the pulsations of these pulsars varied. And this is something that was announced back in June of 2023 of this year. Radio astronomers think they've seen a very low frequency background of gravitational waves. And we don't know what's causing it, but it might be to do with the things that Amanda talked about, very supermassive black holes coalescing and forming that. But I won't say more about that. So what is next? What have we got to look forward to in the future? Well, we're going to have more and better detectors. The Japanese are building a detector. In fact, it's beginning to take data now, and they're building it inside of a mountain in Japan. So I've already mentioned some of these detectors, the LIGO Hanford and the LIGO Livingston. The Virgo detector has already played an important role in all of this, and that's in Italy, and it's a joint effort between many European countries, including Italy and France. And there's also a plan to build another LIGO detector in India. This is important because the more detectors you have, the more confidence you can have that you can see signals, you can see smaller, fainter signals, but also, and I've not spoken about this much, you can sort of triangulate better to get better directional information from where on the sky the signal is coming from. So it really will be very useful to have an improved network of gravitational waves observatories, because then when we see something in gravitational waves, we can more accurately tell our astronomy colleagues where to point their telescopes to try and see it. Another thing that's coming up is a really ambitious plan to do something a bit like LIGO, but to put it in space. So this is called the LISA project. So LISA is another acronym. It's Laser Interferometer Space Antenna. The idea is to put 3 satellites in an orbit, and they each get connected with lasers. So it's as if you sort of got 3 L shapes, because it's it's a triangle with 3 vertices. And because it's in space, you can make it really, really big, arm lengths of order, I think it's order hundreds of millions of kilometers. And this would make it very good at measuring low frequency gravitational waves of just the right sort of frequency to look for the supermassive black holes that Manda was talking about. So the black holes that we've detected with the ground-based detectors like LIGO and Virgo, they've typically got masses of a few tens of solar masses. With this LISA project, you'd be looking at much, much heavier masses, millions, tens of millions, hundreds of millions of solar masses. And we hope that will launch sometime in the next decade, and it's looking very likely that it will, and the funding has been approved for that. So I'm nearly done. In terms of looking forward to the future, I would say that this has been a big success story, but I don't think we've yet seen anything totally unexpected. We've not seen anything where we thought, oh my goodness, why didn't we think of that? Whenever people have looked in completely new physical regimes before, they often have seen very surprising and peculiar things. So we hope we hope that in due course we'll get some big surprises. And with that, I'll stop there.